In this video, we are going over how we use matrices for linear transformations. This is chapter 6.3. Our learning objectives for this chapter and set of videos are to find the standard matrix for a linear transformation and to find the standard matrix for the composition of linear transformations and find the inverse of an invertible linear transformation. So in the first video here, we're going to see how to find the standard matrix. In the next video, we'll see how to find the standard matrix for composition of linear transformations. Then we'll see how to find the matrix for a linear transformation relative to a non-standard basis. And throughout the videos, we'll see how to prove results in linear algebra using linearity. So let's talk about why we use matrices for linear transformations. So the big answer here is because of computing. So matrices give us ability to do more with computing and to do calculations faster with computing. So think about which representation of T that maps R3 to R3 is better. So the first representation is T as a function where you've got the T of x1, x2, x3 represented by the first component being 2x1 plus x2 minus x3. The second component here being negative x1 plus 3x2 minus 2x3. And the third component being 3x2 plus 4x3. Or we can equally represent this function T as matrix A multiplied by column vector X that is x1, x2, x3. So if you take a look at this, you might notice, hey, the coefficients here from my first parts of the function show up in the first row, and my coefficients from the second component of the function show up here in the second row, and my coefficients from the third part of the function here, the 3 and the 4 with the 0 for x1 show up in the third row of the matrix. So you can imagine, oh yeah, if I do my matrix multiplication, I'm going to end up exactly with the same function. So the matrix representation, matrix A times vector X, is simpler to write, simpler to read, and easier to enter into a computer. So here's a discussion thread from Stack Exchange. You can go search out the discussion, and there's many other discussions online. But I really wanted to go a little bit more in depth about why does expressing calculations as matrix multiplications make them faster? So here's a response that got 20 upvotes here in Stack Exchange. Stack Exchange is a website where folks talk about computing, and sometimes math topics come up and the overlap between computing and math. So it's a fun and oftentimes controversial posts show up in the discussions. It's kind of similar to Reddit, but more programming based. So I thought this was a really good response explaining all the ways that we have advantages using matrices. So we're gonna just talk through this quickly, and then you can go back to Stack Exchange and read more in depth if you like. So the poster said, this may sound obvious, but computers don't execute formulas, they execute code. And how long that execution takes depends directly on the code they execute and only indirectly on whatever concept that code implements. Two logically identical pieces of code can have very different performance characteristics. So some reasons that are likely to crop up in matrix multiplication specifically are first, using multiple threads. So they make the point that there is almost no modern CPU that doesn't have multiple cores. Many have up to 8, and specialized machines for high performance computing can easily have 64 across several sockets. So if you're doing calculations for big data or to run some sort of code, you are most likely outsourcing that to a CPU that can have up to 64 cores to do your performance for you. If I'm running something in a big data set, I ask for time on one of the big servers at UC Berkeley, and I set up my code to run in the middle of the night so that I can get that strong computing power. So that's the kind of thing you might do in a career as a computer scientist. So you would want to write matrix multiplication in your code. Using SIMD instructions, this is also known as vectorization, but different sense. So they talk about how you can give one instruction so that it registers in parallel with a matrix. Making smarter use of the cache. So memory access are faster if they're temporally and spatially coherent, and that is basically consecutive accesses are to nearby addresses, and when accessing an address twice, you access it twice in quick succession rather than with a long pause. Using accelerators such as GPUs, so these devices are different from CPUs, and programming them efficiently, it's really kind of an art form, and matrix formulas can help you do that much more efficiently. You want to distribute the work over several machines. So if you're working in supercomputers, this is very important. So matrices can help you do this. And then just smarter algorithms. So for matrix multiplication, in a simple, what we call O of n to the third algorithm, which you'll study that more if you take discrete math or if you take computer science class, but essentially kind of computing time. Properly optimized with the tricks above are often faster than the subcubic ones for reasonable matrix sizes. So you can investigate more of why we often use matrices in coding, but that's sort of the gist of section 6.3. So let's go back to theorem 6.1. So from part 4 of theorem 6.1, we saw this relationship. If V is a linear combination of V1 through Vn vectors, then T of V is T of C1 V1 plus C2 V2 added through Cn Vn, or in other words, T of that linear combination. And then we can pull the scalars out front. So we can have C1 multiplied by T of V1 plus C2 multiplied by T of V2 added through Cn multiplied by T of Vn. So this says that a linear transformation T mapping V to W is completely determined by its action on a basis of V. So in other words, if V1 through Vn is a basis of V and T of V1 through T of Vn are given, then T of V is determined for any V in the vector space V. So this is the key idea to representing T by a matrix. So we're going to make use of the standard basis. So recall that the standard basis for Rn in column vector notation is this, 1 followed by n minus 1 zeros, and then a 0 with a 1 followed by remaining zeros, filling up the n column spaces, and so on until we get to the vector that's all zeros with a 1 in the bottom row. And so these are our standard basis vectors that we call E1 through En. So we're going to use those to construct our matrix that is going to be the matrix representing a transformation. So theorem 6.10 is about how we construct a standard matrix for linear transformation. And it's called a standard matrix because we use that standard basis E1 through En here. So T of E1 is going to give us values that we're going to call A11 through AM1. And similarly through T of En, so we're taking the transformation and acting it on basis vector En, we're going to get A1n through AMN. And then we're going to put these columns together to form matrix A here. And you saw earlier, we didn't really even need to go through this because we were able to really easily see in our example that matrix A essentially corresponds to the coefficient of the linear transformation value. So you're going to get pretty fast at constructing these matrix representations if I give you the linear transformation. Because of the ease of the basis vectors, that's what allows us to see. Because remember, the 1 in the matrix basis vector that's going to correspond with 1, 1 is in the same spot as in the linear transformation. So once we get our matrix A, it's going to be such that T of V is the same as matrix A multiplied by vector V for every vector V in Rn. And so we call A the standard matrix for our linear transformation T. So let's take a look at the proof. You can choose any vector V that's a combination of V1 multiplied by our E1 from the standard basis through Vn multiplied by En in the standard basis. And these V's are the values V1 through Vn that would be the real numbers for each entry in vector V. Okay, so we're treating them like scalars here and using that property of linear transformations that we can pull the scalars out front. All right, so we have said that T of V is T of V1 E1 plus V2 E2, so a linear combination of the standard basis. And then we're saying because we're treating these V1 through Vn as scalars, we're pulling them out front because they're the individual values numerically from the vector V. All right, so then taking this vector V, V1 through Vn values, well, we can say matrix A multiplied by V1 through Vn as a column vector. And then we get essentially the M rows corresponding with the linear transformation. And then we can break it out by the V's using kind of our coefficients here as columns. So we could say, okay, V1 times the column A11 through AM1, and similarly all the way through taking that last column to be Vn multiplied by the column A, 1n through AMN. And that's just V1 multiplied by the transformation on standard basis E1 all the way through Vn multiplied by the standard basis T acting on the standard basis En. Okay, so that's why we're able to say that A of V is equal to the transformation T acting on V for every vector V in Rn. And so this is the proof of why we get to say A is the standard matrix for T. So let's take a look at a couple examples here. So in this first example, we're going to find the standard matrix for this linear transformation in R3. T maps R3 to R2. So the linear function here is T of x, y, z equals x minus 2y in the first component of R2, and then 2x plus y in the second component of R2. So you can do this either in vector notation, as we see here on the left, or in matrix notation, as we see here on the right. So in vector notation, T of E1 is going to be T acting on 1, 0, 0. And so if we plug in our values, we get out 1, 2. If we do this with matrix notation, we're going to do T acting on the column vector 1, 0, 0, and we get out 1, 2. Then we see T of E2 is T of 0, 1, 0. I'm plugging those values in, we get negative 2, 1. And we're just plugging the values into linear transformation T given up here. And then T of E3 is T of 0, 0, 1, but the entries here are x minus 2y and 2x plus y. And so since we have zeros in both x and y and a 1 in the z, we get a 0, 0 here when we map to R2. And then you can see the corresponding matrix notation on the right. And so following theorem 610, these columns of A consist of T of E1, T of E2, and T of E3. So this would be our matrix A here. And then here's a little remark that's important. So as a check, note that A acting on X, Y, Z is 1, negative 2, 0, 2, 1, 0 multiplied by X, Y, Z, which just works back out to be x minus 2y in the first row. So see, we're mapping the first entry formula to the first row, and then the second entry to the second row of the matrix. So notice you can always check and verify that you've got the right formula here. And let's look at another example. So in this example, our linear function is now mapping R2 to R3. So T of xy is going to be 2x minus 3y in the first entry, x minus y in the second entry, and y minus 4x in the third entry. So then as matrix representation, we can say, okay, T of E1 here, because E1 in R2 is going to be 1, 0, is going to be 2, 1, negative 4 written as a column vector. And then T of E2, which is 0, 1 here in R2, our second standard basis, is going to be, or a second standard basis vector, I should say, is going to be T of 0, 1 is negative 3, negative 1, 1. So we put these two columns together here to get our standard matrix A. But you might say, well, wait a minute, I can see these are just the coefficients mapping each coefficient from each entry to a different row of the matrix. So you can see you won't need to necessarily go through these calculations if you can see right away, oh yeah, I just pulled the coefficients out. Notice in this last entry, the y minus 4x, the minus 4 still goes with the x here, and the 1 goes with the y. So just make sure if x and y aren't written in alphabetical order that you do the proper rearrangements. All right, let's look at another example. We're going to find the standard matrix for the linear transformation T that's a reflection of the line y equals x in R2, and use A to find the image of the vector 3, 4 and sketch the graph of V and its image T of V. So we say A is going to be T of E1 and T of E2. And so since our equation here is this reflection, y equals x, then we end up with a reflection of what we think of as the identity matrix. And so T of V equals T of 3, 4. So if we take our reflection matrix 0, 1, and 1, 0 and multiply that by the column vector 3, 4, we end up with 4, 3, which is just x and y flipped. And so we can see our visual here. So if you've got values at 1, 0, that's going to reflect to be 0, 1, and here's y equals x right down the middle. And then if you've got values at 3, 4 up here, and T of V is down here, that is 4, 3. And again, our line through here is y equals x, and we've reflected about that. Okay, so a little practice is going to enable you to determine the standard matrix for linear transformation, just like we saw in example 1 and the other examples, just by inspection. So this is what we talked about. Notice the first entry of this function, x1 minus 2x2 plus 5x3. Well, we can just map that with the coefficients of x1, x2, and x3 to the first row of A. And then similarly, if the second entry is 2x1 plus 3x3, we can map that to be a 2, 0, 3, 0 because there's no x2 here in this entry. In the second row of our matrix A, and then for our third row of matrix A, we can just look at the coefficients in the third entry of this standard matrix. So we've got 4x1 plus x2 minus 2x3. So we're able to put a 4, 1, and negative 2 here in the third row of matrix A. So you don't have to go through plugging the standard basis vectors E1 through En into the function T, because you know you can just look at the coefficients to construct this standard matrix. So in the next video, we're going to look at compositions of functions.